that today is the last official lesson of the geometry curriculum. Y'all excited? I thought you'd be more excited than this. Yes.
What is
monotony? Whatever you said.
Monotony. Like boring, doing the same thing over and over again.
You didn't know either.
Wait till Sandra gets back. So today is the last official lesson of the entire geometry curriculum. That's not to say we're done. We still have EOC review next week. After that, of course, the whole week of EOC testing, which we will be doing a project during that week. Then after that, we're going to be starting to prepare for Algebra 2. So you still will have homeworks and we still will have lessons, but we're done with geometry.
We're going to have a party?
No.
Well, I'll think about that.
Oh, wait, they filming you.
Okay, so our last lesson is on tessellation.
Today's the 24th, right?
Today is the 24th. So, tessellations, like I said yesterday, when you start getting tired of the sound of my voice and start looking around the classroom, that's what these things are. You could ask me all year, are we going to do this project? We going to do this project? Yes, we are going to do this project. Not right now, but we are going to do this project. This is what we're going to do during EOC testing. We're going to do this project. So these are all examples of tessellations. The ones on that side are all examples of tessellations. The one covering the back wall. Those are all examples of different types of tessellations. Okay? So let's get some background knowledge of it. So when we're ready to do the project, that we can go ahead and know what we're doing. Okay, so tessellation. Everybody say tessellation.
Tessellation.
Yes, okay. Tessellation. A tessellation is a repeating pattern that completely covers a plane with no gaps or overlaps. The measures of the angles that meet at each vertex add up to 360 degrees. So once again, the whole point is that it has to cover the entire plane. So that's why you see on all of these examples, they cover the entire. Then you can see the entire paper covered on all of them. Like, what do we do when we walk in the room for the past, like, 7 months? Okay, so notice how you don't see any gaps or any kind of overlapping, and if you do see gaps, then it means it's probably wrong. So, yeah, so make sure it has no gaps, no overlapping. And usually if there is a gap, it's usually going to be filled by some type of polygon. So there's a subcategory. There's subcategories for tessellations. So one type of tessellation will look something like this. Here we have squares. They're all right next to each other, on the bottom of each other. They're moved around, but they're all squares. So in this one, this is called a regular tessellation. And regular tessellations are formed by congruent regular polygons. So any type of regular polygons, what does regular cover again? No. Regular. What makes a polygon regular?
Oh, outside.
What makes a polygon regular? I know we talked about it maybe in December, a little bit in February. Nobody, what makes a shape regular?
Concave would.
Concave is types. Same size what? Congruent angles, thank you, and thank you. Congruent sides and congruent angles. All the sides have to be congruent to each other, all the angles have to be congruent to each other. That's what makes it a regular polygon. It's like a square is an example because all the sides have to be the same and all the angles have to be 90. So that's an example of a regular polygon. But it can be any polygon, but it just has to have the same exact length of sides and the same exact size angles. So that's one type of tessellation. Another type of tessellation, if you look at this picture, you have two different types of polygons here. We have octagons and squares. Okay, so they're all mixed up together. So this has, clearly it has more than one regular polygon. So this is called a semi or semi, a semi-regular tessellation. And it says a semi-regular tessellation is formed by two or more different regular polygons, so underline two or more different regular polygons. The same number of each polygon must occur in the same order at each vertex. So you're going to see the same pattern over and over again. Even though it may be different shapes, different types of polygons, you can still see the same pattern. And remember, it's two or more, so it can have more than two, but it has to be at least two for it to be a semi-regular tessellation. Okay, so that's dealing with the types that make up those tessellations. So those aren't the only kinds. Those are only when we're dealing with polygons. There's some other ones when we have different kinds of patterns. So that's more what you see here. Like this one is an equilateral triangle, but the rest of these are some kind of funky patterns. And 9 times out of 10, those are kind of easier to do than doing the regular shapes, because 9 times out of 10, it's hard to cut, you know, a perfect polygon. So that's why we have some funky stuff going on up here. So it's created by, if you look at this, what are they doing with each one? How are you getting to this new picture?
Put it in.
Watch my hand. What am I doing? Thank you. So if I'm sliding them, exactly, I'm translating. So what I'm doing is translating each picture. So a repeating pattern has translational. It has translational symmetry. Because if you look at the picture in this box, that's all they did with these little patterns here. All they did was slide them over and create the same exact pattern. So it says, a repeating pattern has translational symmetry if it can be translated such that the image coincides with the pre-image. So can it be bigger?
No.
No. Coincides. It has to be the exact same size, exact same shape, exact same figure, exact same picture. Okay? So it has to coincide with the pre-image. So, question. What type of transformation, we've learned 4 so far, what type of transformation cannot be a part of a tessellation? A dilation. Thank you. Because doesn't dilation change size?
Yes.
Makes it bigger and smaller. So once again, it says it has to coincide, so therefore you can't change the size of it. Okay, so that's translational symmetry. So next one, it says, well, let's look at the picture first. You look at the picture, what are the shapes that you see here? A triangle and what?
Trapezoid.
There we go. Triangle and a trapezoid. The ones in white are the trapezoids. The black ones are going to be your triangles. Now look at what they did to form that pattern. Really, all they probably did was take the trapezoid and move it. And when they moved it, it created those triangles. Okay? So if you look at the triangle or the trapezoid here, as opposed to the trapezoid on this one, it's upside down. So they basically did what if it flipped over? It's a reflection. So when we did, it was either symmetry or compositions of transformations, I don't remember which one. We had something called a glide reflection. When we did 2 transformations in one, we did a translation and we reflected it. So that's what this one is. It's a pattern with glide, reflectional symmetry. A pattern with glide reflectional symmetry coincides with its image after a glide reflection. Okay? Alright, so that's basically the basics of tessellations. So now let's apply some of those things. So if we go back up to the original box, it says the measures of the angles that meet at each vertex add up to 360. So let's look at this box. Here we have squares. Of course, you know in each square all the angles are 90. So that's why they have 90 degrees all around the center. So where those vertices meet of those different polygons or those squares, they're all 90 degrees. So they already did this one basically for us. They added them all together, and of course 90 plus 90 plus 90 plus 90, or 90 times 4, it equals 360. So as long as it equals to 360, then yes, it does tessellate. Okay, so yes, it tessellates. What's our next shape? It's a hexagon. Question. If I kept repeating that pattern of a hexagon, what real world object would it create? Thinking caps. Yeah, look at that. Think about it. Whenever you see up close images of beehives, aren't they all made up of hexagons?
Yeah.
So that's a real world image. So that's actually tessellation.
You said what object?
Didn't even know. Look at that.
You said what? Never mind.
Huh? Nothing? Okay. Alright. So I'm sure that we might have forgotten the formula for finding the some of the angles of it inside of a polygon. So let's say we forget it for EOC 2. So we go ahead and remind you of how you can find it if you don't remember the formula. So we pick a vertex and we triangulate. I like that word, it makes us sound educated. Triangulate. We're going to triangulate the polygon. So that means you just draw and connect the vertex to all the other vertices in the picture to form triangles. How many triangles do you have? How many triangles do you have? 6.
It's 4.
There's 4. How do y'all see these other numbers? There's 1, 2, 3, 4. Right? Okay. So how many degrees is in each triangle?
180.
180. So if I really wanted to figure out the sum of the angles, all I have to do is do 4 times 180. Bam, there's my answer. So that's if you don't remember the formula. So of course we're going to go over the formula. The formula, I'm sure, like I said, you might recognize it once I show it to you. That's when we do n minus 2 times 180 divided by n. So we're familiar now? Okay? That's when we're trying to find one angle of the polygon. What does that n stand for?
Sorry.
Yes, the number of sides. So if this is a hexagon, of course, what am I going to plug in? 6. So we have 6 minus 2 times 180 divided by 6. Since you have your phone out, why don't you go ahead and use your calculator on it? Calculate that for us. Thanks. Congratulations. She gave it to us. It's 120, but thank you, Alex. Keep it out, though. We're going to use it again. So it's 120, 120, and 120. All around that center. So now we just need to see, does that add up to 360? 120 times 3, or of course you can do 120 plus 120 plus 120. So does that equal 360?
Yep.
Yes, it does. So therefore, does this picture tessellate?
Yes.
Yes, it does. Questions about that? Okay, so I want you to try the next one by yourself. So they don't have markings on here, so what I want you to do is assume that all of these triangles at the top are equilateral triangles. So thinking caps, they're all equilateral triangles. How many degrees are their angles? 60. Yes. So you know that these are 60-degree angles. And of course, the square is going to have them. Okay, so figure out if that tessellates. Anybody know where Taylor's been?
She was in the hospital and she at home. Oh, what happened? Yeah.
Oh. Oh.
Who's Taylor?
All right, does it tessellate? Yes, it does. So I put it into groups. 60 times 3 plus 90 times 2. So 60 times 3 is 180, 90 times 2 is 180, 180 plus 180. So yes, it does tessellate. So now let's use some of those same things to figure out if we're just given the figures, it's not set up to where it's tessellated, and it's decide if those pictures or those polygons can actually be used to tessellate the figure. So one thing, we know that when we add them all up around the central angle, all the vertices have to add up to 360 degrees of those angles. So what we're going to do is we're going to have to figure out the same exact thing. We need to figure out one of the angles of each polygon. So of course we know the triangle is going to be 60. This is a pentagon, so when I set up my formula, I know that I have 5 minus 2 times 180 divided by 5. Alex, you're on. What do you get? Use your calculator. You have your phone right there. 3 times 180 divided by 5. Yes. So I know one angle in our pentagon is 108. So for these, since like I said, we don't know what it's going to look like when it's tessellated. So all we're going to do is we're going to take those two angles and add them together. 108 plus 60, which gives us 68. So since we know ultimately it's going to have to relate to 360 somehow, in order to figure out if it's going to tessellate, we need to divide 360 by the two angles that we have, the sum of the two angles that we have. So we would do 360 divided by 168. Hit it. What? I was telling
168?
360 divided by 168.
2.14.
Yes. So you get 2.14. So when we have 2.14, that doesn't divide evenly. So if it doesn't divide evenly, then that means it's not going to tessellate. So, okay, it's not going to tessellate. I'm just going to put doesn't divide evenly. Okay? So now I want you to do the same thing for this one. And let me give you a hint. This is a hexagon. We've already done a hexagon in the previous example, so you should know how many degrees it is. So go ahead and do the same thing. So once again, let me recap. We found the angle, one angle of each of the polygons. We added them together, and then we divided 360 by that number to see if it divides evenly. If it does divide evenly, it tessellates. If it doesn't, it does not tessellate. It will not make a tessellated picture. Angles. That'd be 4 times 180. That's about
180 times 60.
What? Here it is anyway. Let me get Same shape. The triangle.
Yeah.
You can do it like that. So you know that you have 4 triangles, so just multiply 4 times 180. So find the angles, add them together, divide 360 by whatever that number is. 360 by the angle added. Yeah, that's not super cool. Tell my baby, text her back later.
He's already.
That was kind of funny. We did the same thing up here. It's supposed to say it's like number. It's the hexagon. It's the hexagon. So I know where we got 60 from. Okay. Did it divide evenly? Yes, it did. So what does that mean?
Yes.
Yes, it tessellates. So when you figure this out, and I try to give you a hint, we just did the hexagon right there. These are 120. So that means this is 60. So 120 plus 60 is 180. 360 divided by 180 is 2. So yes, I'm just going to put divides evenly. Okay, on these, all we're going to do is figure out, are they regular, semi-regular, or neither? So that's when we're using these that we did, the subcategories. Remember, for the regular tessellations, you know you have to have congruent regular polygons, one congruent regular polygon. For the semi-regular, you have to have 2 or more regular polygons. So once again, figure out which ones are regular, semi-regular, or neither. Hint, there's going to be one of each. Just take a second and look at that. Figure that out. So after we're done, Tamina, you're going to give me A. Rodolfo, you're going to give me B. And today, you're going to give me C.
Who?
So be prepared.
So who's Rodolfo? I'm done.
Unsure, look back up at the definitions at the top. Huh, you're done, huh?
I was done. Just couldn't figure it out.
Nina, what'd you get for A?
Semi-regular.
Yes, that's semi-regular. Don't forget the semi-regular has 2 more polygons. Which polygons do you see in A?
Hexagon, square, and triangle.
Yes. So you see 3 different polygons, hexagon, square, and a triangle. They do not overlap. Of course, it's supposed to give you the illusion that it's overlapping, but those shapes are not overlapping. Okay, B, Rodolfo, what'd you get? Yes, B is neither. A lot of you put either regular or semi-regular for that one. That is neither. Remember, these are supposed to be regular polygons. What shape is that? Yeah, those are trapezoids. If you look at it from this way, there's your parallel bases. Those are trapezoids. So that's not going to fit either category. Is it tessellation? Yeah, it is. But still, it's not regular or semi-regular. C. Today. Yes, that one's going to be regular, of course. All of those are triangles. They're the same triangles. They're just different colors. So that doesn't matter. It's just the fact that it's the same exact polygon. Okay, let's look at the back. At the top, all it wants you to do is just shade in the shape that's being tessellated. So go ahead and shade in the shape so that you can see exactly what's being tessellated. And then think about our 4 transformations that we have learned. Rotations, reflections, translations, dilations. It wants to know what transformations were used to make that tessellation. So look at the picture. So all that happened is it went bam, 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 bam. So what am I doing?
Sliding.
I'm sliding, which means it's a translation. So that's the only transformation in that one. The only transformation is a translation. It cannot be a reflection, because if it was a reflection, it would have this curve at the top. So these at the top aren't curves. So that can't be a reflection. Okay, so that's not the same exact image. Questions about that? Okay, so I'm going to give you some pad paper, and I also want you to keep it for your homework tonight. There is one shape that you are going to have to tessellate on your homework. So make sure that you keep it. So when you get your piece of patty paper, of course, feel it for the rougher side. That's the side you're going to write on. And you're going to trace that image that's on example 4. Now, do you know who Rodolfo is?
I know about Rudy, that's why.
Oh, should I call you Rudy? You never told me that. Huh? Translation. Because all it did was slide across the paper.
Okay, you're not doing your work.
Yeah, I guess you came late, so I told the kids, they have a nickname. As long as it wasn't Pookie or, Boo Boo, then I can call you your nickname. So go ahead and trace it on the rough side. So once you traced it, it wants you to tessellate the picture. So that means all you're going to do is you're going to take it and you're going to do different things with it in order to get it to repeat. Like for instance, I could take it and I could, let's see, if I wanted to turn it that way, I can do that image and then turn it again and repeat it. Or if I wanted to flip it over and make life a little bit easier, I can reflect it. And then I can have my shape right there. Now remember, the key to tessellating a picture is that it can't have any gaps or overlaps. So you can take that image and then keep turning it different ways as long as it meets up and you have no gaps or overlaps, then you have created a tessellation. So you can turn it like this if you want to. I mean, you can really do it differently. Or if you trace back over it on this side, it'll make that shape. So you just have to go over it a little bit. We're going to do the same thing. Keep turning different ways so it'll meet up. Sometimes it's easier with a pen, sometimes it's easier with a pencil. Okay, so that's one example of mine. Okay? So Some other ones that I've done today, I kept going and I made it look like this. There was another one that I did where I had it going straight down, which I don't see right now. Yeah, I don't see it right now, so let's not waste the time. So it can be in different ways. But the next question says, what transformations did you use? So in order to get your shape, however you tessellated, because it could have looked different. There was more than one way just to tessellate this picture. What could it have been? What could you have done? You could have reflected it. What else? Translation. Anything else? And a rotation. So it just depends on how you did yours. So I used all three. Okay, let's look at example 5 quickly. It says Susie created the design below, figure A. She then used the design to create pattern, figure B. What type of transformations did Susie use to create this pattern? So this is a tricky one. Look carefully. Don't get tricked. While you do that, I'm going to pass out your homework. So we're not packing up yet. I'm doing homework.